Question 21. A star A and B emits both their light at the wavelength 650 nanometer and 480 nanometer respectively. Star A had twice the radius of the star B for the ratio of the luminosity of the stars. Luminosity radius relationship. Looking for some equation in this formula sheet. Light wavelength, we know their wavelengths, so we can determine their temperature using VN law here, 2.9. And then using intensity, looking for the topic 12, the astrophysics part. Yeah. We know the wavelength, therefore we can determine the temperature T, and then here, using this formula, the luminosity here, actually the power in the topic 8, which is sigma times, where's that? Here. E, the coefficient for black body is 1, okay? And Stephen Boltzmann constant and area of the star and the power for the temperature. Luminosity is actually this power P, okay? So from the wavelength, we determine the temperature and then plug the value of the temperature into this equation of luminosity. Divide, of course, the value of luminosity L must be measured. We can measure the luminosity by using a telescope, a device on a space telescope. We collect the amount of energy that the telescope receives in like 1 minute, okay? And then divide 60 seconds to get the amount of energy that it received in 1 second, which is the power, okay? And then, yeah, that is the power that we receive, which is the apparent brightness, B, not the luminosity. Apparent brightness. We must know the distance to that star so that we can determine the luminosity. We cannot measure the luminosity directly, can we? How to measure the luminosity of a star? Okay. According to this summary, we must know the distance to that star. Normally, they use the apparent brightness and luminosity to measure distance instead, not. Okay, what is luminosity and how it's measured? Or last time we studied about the Cepheid variable, remember? We use a rule that was already discovered, the graph of Cepheid, describing the relationship between their luminosity and their period of the change of its intensity, meaning we can calculate their Cepheid here, the luminosity of the Cepheid.
Okay.
We cannot measure the luminosity directly. The only thing we can measure directly from the Earth is the apparent brightness, B here. By a device collecting the energy from the star, divide the amount of energy by the time we collect that, such as 1 minute, and divide the area of the device collecting the energy like a solar panel, okay? The area of that solar panel, so that we can calculate the B, the apparent brightness. But for the luminosity, so that is the reason why we have to use the Cepheid star below here. So it is so important by this discovery, because we cannot determine directly the luminosity of other fainter star, not the Cepheid. Okay, returning to the question, try the radius, how do we compare the luminosities? Yeah, they're comparing the luminosity, LA and LB. The radius, twice the radius here. One star is twice the radius compared to the other star. Try the radius, try the answer. Sorry, my fault. I didn't read that. Okay, so using this luminosity equation, the area A in this equation is the area of the sphere, 4 pi r square. We have the VN law, the lambda max. We increase the size of the text. lambda max multiplied with the temperature is equal to a constant 2.9 times 10 to minus 3, and you can denote that by the letter K.
Yeah.
Okay. TA is K over lambda A, which is 650 nanometer. You don't need to convert to the meter normally. If you do the convert, meaning you need to multiply with times 10 to the negative 9 from nanometer to meter. Okay,
Okay.
this is TA. TB is that constant divided by the wavelength 450, right? Times 10 to the negative 9. And then comparing the luminosity, because that equation, luminosity L, forgot it, L sigma time of Stephen Boltzmann constant time the area and time the temperature, sigma area and temperature power 4. This is the only equation that link the temperature with the area, which is 4 pi radius square. Because we are asked about the ratio of the luminosity. We are asked to find LA over LB. Okay, so this is the only equation available to use. Sigma, the area A, temperature A, power 4. Sigma, area B, temperature B, power 4. Okay.
Yeah.
And we can simplify sigma, the area is 4 pi RA square over 4 pi RB square. We can also simplify for A. And the temperature A is K over 650 times 10 to the negative 4, power 4. The other thing is K over 450 times 10 to the negative 9, power 4. So you don't even need to use the conversion, negative 9, because the power is the same, 4
Yeah.
and 4, so they can simplify each other. Okay, so but if you want to calculate the temperature in the unit of Kelvin, you must convert the unit of the wavelength to the meter, which is the SI unit. Okay.
Okay.
So we can also simplify the K, which is 2.9 times 10 to negative 3. So that's why we don't need to actually calculate the temperature, but just calculate the ratio. Okay. So this is the result. RA is twice RB, right?
Yeah. Star A
Yeah,
is
twice. Okay. So twice RB here, square, divided by RB square. And this is 1 over 650 power 4 over 1 over 100, 450 power 4. And the result is RB square here, cancel out with RB square at the bottom. So this is 4, 2 square is 4, okay? Multiply with 450 over 650, all powerful. This is the result, okay? So it simplifies a lot of calculation if you do individually, each step by step, okay? 450 divide 650, and then power 4, and then multiply with 4. The final result is 0.9, which is different from the answer, right? There's something wrong. Oh, sorry, that is 480, not 450. 480 here, 480, 480. 480, yeah, over 650, and then multiply with 4,
yeah.
480 divide 650, and then power, where the power sign here, power 4. I need to put a bracket for the power of the ratio. Yeah, power 4, and then multiply with 4. The answer is 1.19.
Yeah. I can
1.9 or 1.2.